All right, let's go ahead and get started. Many of you are still running into problems with the virtual machine. I think it's running too slow for one thing. I think I have found a solution. Since I sent the first email message today, I tested that and it didn't work, on the platforms that I tested it on. So I went around to try to find another distribution or another version of QEMU, and I found 0.15.0, which is one version below the one that I originally distributed in the class. And that one came with both a 32-bit and a 64-bit emulator. And I tested that with Windows XP, 32-bit mode, and that worked fine. So today what we'll do is we'll test it in the 64-bit mode and see whether there's a speed gain. If so, you guys can all switch over. There's no need to redo anything that you have done so far except for the batch file. But I have also included my batch file inside the zip file. So for your convenience, you only have to move your disk.qcow2 file over, and that's it. That should be the only thing you have to do. Okay? Yes?
And the ISO?
The ISO is, it should be sitting somewhere other than in the QEMU file if you follow my directions. So, and if you did not, you can just copy that file over too. Okay? So we'll go ahead and give this a try. Yes? Go ahead.
You said it worked well in 32-bit, this new version?
But only on a 32-bit Windows, 32-bit Windows system.
Okay.
The reason why it's running so slow, why QEMU is running so slow, is because when you run a 32-bit app in Windows 64-bit, it is actually automatically running inside a virtual environment. So effectively, we were running a virtual machine inside a virtual machine already, and that's why it is so slow. So today, we'll give this a try and see whether it is any better. I have already tested the 32-bit version, and it worked fine in Windows XP. So now it's time to test the 64-bit. Alrighty. That didn't go well. Okay, what is the problem? Could not open disk qcow2. Okay, so let's take a look again. Nope. Wrong folder. All right. Where's my qcow2? Oh, it's missing. No wonder why. Oh, I remember why. There were two of these. One is a copy of the other one. The one that we just went into is the template that I used to create the zip file that I put onto Moodle, and I intentionally did not include the qcow2 file because you have your own qcow2 file already. So that's why that's the problem. So this one should work because I have my qcow2 file and everything else is here. So double click, starts right up, and does anyone want to time it? I'll time it.
Thanks, Mom.
Actually, since everything is being recorded, I don't really have to time it because I can always watch my video again and time it later. That's the nice thing of recording everything is, I don't have to do anything like, real time. I can always do it afterwards. Does it seem any faster? No?
Is it passing VMX or whatever the AMD equivalent is to the kernel to enable hardware virtualization acceleration?
That I don't know. But at least it's not running in a virtual, we are not stacking virtual machines. So that should help. I think it's running faster already. And I did not even start up in text mode, so we can actually see how fast it can bring up the GUI. And while it's doing this, we'll go ahead and log in. Let me ask you guys another question. Does everybody know how to get into YouTube and find recordings of this class?
Yep.
Okay, very good. Because that is a very useful resource, not only for you, but also for myself. because sometimes I forget what I talked about in the previous class, so I can always watch the last few minutes of my previous lecture to bring myself up to date. Like, oh, okay, so that's where we stopped last time. And since the other one is starting up, I'm going to start with the new homework assignment. Yay! Binary add. Well, I should actually change the name of this homework assignment. It's just binary add. Subtract will be another homework assignment. So this one is just adding. All right. So you can do this homework assignment in a text file. In fact, I want you to do it in a text file so that my script can process it easily. You do not need to save the text file in Unix text format. You can just save it in Windows/DOS text format. My script can automatically convert that or handle that part. You will have several lines. The first line is your 7-digit student ID in decimal. So you don't need to do any base conversion first. The following lines must have exactly 16 bits. Okay? One binary digit is 1 bit. The second line is the binary representation of the first 4 digits of your student ID. Okay, so pick the first 4 digits, as a decimal number, convert it to a binary number, and that becomes the content of the second line in the text file. Now, many of your student IDs, will not fill in all 16 bits. It does not require 16 bits to represent a number. That's okay, just pad zeros on the left-hand side. Okay, just make as many leading zeros as necessary to fill up 16 bits. The third line, the line following that, is the binary representation of the last 4 digits of your student ID. So yes, one of the digits is double counted. It is the least significant digit of the second line, and it is the most significant digit of the third line. Is that okay so far? Okay. The fourth line is the simple sum of the digits using the rules. 1 plus 1 is 0 with a carry. 1 plus 0 is 1 with no carry, and so on. So you don't have to take the carry from the previous or the less significant digit for that line, for the fourth line, because that's the job of the fifth line. The fifth line is only used to represent the carry bits from the previous digits. Just exactly like the way we worked on these things on Tuesday. Do you guys still remember Tuesday? We worked on the binary addition. Basically, it's the same format, except in this case you don't have all the add and all the other stuff. It's just all the digits. And the sixth line is the final result. Okay, that's the final sum. And each and every line should have 16 bits. On each line, you can have as many leading spaces and tabs as you want, because they will be ignored. And if you want to have comments, you can put a pound sign, and everything from the pound sign and up and to the rest of the line will be ignored as well. Pound is kind of like slash in C++. Okay, so here's an example. This is a student ID that I just invented. If anyone in this class has exactly this same student ID, it's purely coincidental, freakishly coincidental. The next line is 0283 in binary, because that's the first 4 digits of the student ID. This part, you can just use a calculator. Just use a calculator to do the base conversion from base 10 to base 2. Okay, that should be a pretty easy job to do. Most calculators can do that. If you don't have a calculator that can do base conversion, use the one in Windows. The second one, or the next line, the third line, is 3371 in binary, because that's the last 4 digits of the student ID, and it turns out to be this particular bit pattern. The fourth line is just a direct sum using the rules. 1 plus 1 is 0. 1 plus 1 is a, well, I shouldn't say that. 1 plus 1 is a 0 with a carry, so you have to remember to put the carry on the next line correctly. 1 plus 1 is a 0 with a carry. 0 plus 0 has no carry. 1 plus 1 is a 0 with a carry. 1 plus 0 is 1 without a carry. I would fill this line with all zeros initially, and only when you need to turn it into a 1, then you turn it into a 1. Okay? And in that process, you will fill up both this line, which is a direct sum, and also this line, which is the carry from the previous column. And then this line here represents, this bit adding this bit. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 0 is 0. Now this is an interesting one. 1 plus 1 is a 0, but you have to remember to put a carry here. There are 2 chances that you might have a carry to the next digit. And yeah, go
The
ahead.
numbers in your example are wrong. You used the 3 twice. The first number should be 0028. You used the 3 at the end of the first and then duplicated it in the first and the second.
Yeah.
So you have 3 3s instead of 2.
3 3 instead of 2.
So your first number is 0283. Second number 3371.
That's part of the instruction.
Yeah, but the instruction says you have to pick the first 4 digits.
Oh,
You double
okay.
count the middle digit.
Gotcha.
Yeah. So in other words, the 4th digit, the middle digit is double counted. It's used in the first number and also the second number.
Okay.
Okay. So that's it. That's your homework assignment. You can do it easily with a calculator with this line, and also this line. But most calculators will not give you the middle 2 lines, which is how you get to the final solution. And those 2 lines, obviously, will be used for grading purposes. Just to make sure that you guys can do binary addition and understand the principles of binary addition. Any questions about this homework assignment?
Should we zip it up like our last assignment submitted?
Yes. Yeah, but this one is just a text file.
Oh, just send you a text file.
Just send me a text file. At the end, it will give you an upload interface. Just
Named
upload a simple
anything-
text file.
Named anything specific?
Nope, nothing specific,
Okay,
because you will have logged in as yourself when you turn it in, so I can tell who turned in which file. So that part is not important. Yep.
So does the file have like its own I don't even know how to say this, like signature from where it was
Yes.
first created?
This first line.
Well, no. I mean like the other file that we created, because if we didn't name it or anything.
You don't have to name it in anything because the first line of the file is your student ID, and I can use it to identify who turned in that file to. So, yep.
Does it matter if you do this in your virtual machine or in another operating system?
It doesn't matter. It's just after you turn it in, all I can see is a plain text file.
And the format should be a .txt. Is that what you're looking for?
Well, it has to be a text file, but the extension does not really matter. My script, will not check the extension. It will just check the content of the file. Yep.
On the 5th line, so you're doing carries from the top 2 and then, above
Okay.
it, and then you're doing carries after
Okay.
that as well?
Well, okay. This 0 comes from the previous column, which does not exist. So that's why it's always a 0, because it's already the least significant. The least significant digit.
Right.
This one comes from at 1 plus 1 equals 0 with a carry.
Right.
Now you can also have situations like this one here. 1 plus 1 is a 0 with a carry. So for each column, there are 2 possible ways to generate a carry for the next column.
Okay. Yeah,
Okay.
that's what was confusing me, because above you do 1 plus 0, and that doesn't have a carry.
No, 1
But then
plus
there is a
0
carry there.
has no carry, but then you have 1 plus 1 here that has a carry, so that's why you have to set its carry to a 1.
Okay.
Okay? Any other questions about the homework assignment? It's basically the same format as what we did on Tuesday, except we don't have all the extra lines and the plus symbol and stuff like that. It's just the bits in this case. Okay. Any other questions about this? No questions? Okay, did anyone keep an eye on this one and see whether it's actually faster? No? It's still sluggish?
Well, it's probably faster. I mean, I believe the other one would have been up a bit.
I don't think you can get much slower than it was before.
Don't say that. Do not say that, because the guy who wrote QEMU, actually, I don't know why he would do that, but he rewrote the emulator in JavaScript, so you can actually run the emulator in a browser. I do not know. Just look up QEMU JavaScript, and you will find an article that talks about that. He re-implemented the whole thing in JavaScript so that you can run an emulator inside a browser. Yeah, so it can be slower than this. All right. Let's go ahead and continue. So if this is not any faster, I would just use the text mode of the virtual machine and then use PuTTY to open up additional terminals. I mean, that seems to be the most practical solution, at least at this point. Okay, any questions? No questions? All right. If there are no questions, I have created a new link to another note or module that I have written before. It's called half adding and full adding. Half adding and full adding, which is things that we have done already, but it gives it a more formal treatment. So we'll go back and talk about this after we talk about memory access. We are pretty much done with the story of registers. Basically, registers are not memory, for one thing. Memory is slow, and that's why we need registers to help us. Registers are also not the cache of your computer. Each register is directly addressable by instructions of your processor. Okay? In other words, you can specify this instruction to use specifically this register and that register to provide information for adding. When you're dealing with cache, you cannot really control the caching. Sometimes it's in cache, sometimes it's flushed out, but you have little control over when something is going to be cached. But with registers, you have direct control. The instruction can specifically specify which registers it wants to use. Okay, any questions about that part? Okay, the next note is about memory access. And this one basically just talks about memory addressing. How does your processor get information from memory? And vice versa, how does it store information in memory? This is definitely kind of archaic. It's based on really old, systems that has no DDR capabilities. But DDR is really a fancy trick on top of the old ways of doing things to speed up memory access in burst mode. But basically, if you're not doing burst mode access, even if you have DDR3, it still has to go through the same mechanisms as what is described here. Okay, so what is described here is, even though it seems to be very slow and it does not take into account DDR type technology, it really is still true and still being done in all modern computers. So we'll go ahead and start with memory chips. The main memory of a computer is usually implemented by multiple memory chips. In other words, it'll be sometimes, very seldom, you can find a computer system where the memory comes from a single chip. It can happen, but most of the time it comes from multiple chips. The external interface of a memory chip consists of the following. We have a whole bunch of what we call address lines, and each one appears as a pin on the chip. Does everybody understand what I mean when I say a pin on an IC? It's an electrical contact point on an integrated circuit. Okay, it's just a shiny metallic little tab, from the chip. It has a whole bunch of lines, or a bunch of pins corresponding to data lines. It has one single pin dedicated to read-write control, and then it has one additional pin called chip select. Okay, so all of these are kind of foreign, and we have no idea what it means. But we'll describe the functions of all those lines and all those pins later. Yep.
I just want to ask if it has to do anything with all the copper lines we see on the chips.
No, not the copper lines. Okay, well, since you asked the question, I can just kind of deliberate a little bit on this. when you buy a chip, a IC integrated circuit, regardless of the packaging, it always has some conductors, so that you can attach it to a circuit board. So the more conventional chip looks like this, kind of rectangular in shape, and it has pins on two sides like this, one side and then the other side. So this is kind of like a conventional chip, which has a low density because this takes up a lot of space, just to provide this many connections. So this is the IC itself. It's usually black, because that's the material they use for the casing of the chip, and these are pins. Okay, when you design a circuit board, you will have a socket of some kind, or you can directly solder the chip on the PCB on the printed circuit board. The circuit board itself. Okay, the circuit board under this will have what we call pads. Okay, basically they're copper, exposed, copper, so that you can put the chip or the pins on top of the pads. And when you solder, it is soldering the pin on the chip to what we call a pad on the PCB on the printed board circuit. So now your chip is electrically connected to the printed circuit board. Okay.
It's similar to the lines that has like a RAM chips.
Yes. Well, each one of these is called one line or one pin. So basically, if you look at this one here, you can kind of imagine that some of these are address lines, some of these are data lines. One is dedicated as a read-write line, and one is a chip select. On top of that, you still need power and ground. So somewhere you need two additional pins in this case for power and ground to power up the chip. Okay, but that's kind of like a electrical from an electrical engineering perspective, and not from a software perspective. Okay, so the pins corresponding to the address lines are input pins. Each pin accepts a binary input. In other words, when you look at the address lines, each line can be a 1 or can be interpreted as a 1 or a 0. Typically, when the voltage is high, like 5 volts, 3.3, or depending on the technology, a higher voltage means a 1 and a lower voltage means a 0. But it's usually binary. So, for instance, if a memory chip has A0 to A9 as the address pins, then it can specify location 0, which means all 10 pins are zeros, to location 511 in decimal, because you can have basically all of these pins turned into ones. And I think I did a mistake here, because if there are 10 of these, it should be 1023 and not 511. So I did I did it incorrectly because I miscounted the number of bits. So this should be a 1023 and not 511. Okay. Does everybody understand why there's a mistake? Where the mistake came from? Okay. Now, each location of a memory chip is an individual quantum to access. Now, this is really quite important, because what it means is you cannot choose in software and say, sometimes I want to access a single bit, other times I want to access a whole byte, because that is hardware dependent. If your memory chip is a byte device, then every time you have to access the entire byte. You cannot just say, I want the lower nibble, the lower 4 bits of a byte. You can filter that out, but when you access, you're always accessing a byte at a time. For example, let's assume that our each location is a byte which is 8 bit wide. The data pins of a memory chip must be wide enough to input or output the content of a location. So that means if each location stored in a memory chip is a byte, then we can expect to have 8 data pins, and they're typically numbered as or labeled as D0, data 0 to D7, data 7. Each pin represents 1 bit. Are we doing okay so far? Okay. Data pins are bidirectional, which means sometimes the memory chip drives the line, it specifies the content or the voltage. Other times, somebody else is driving the voltage or driving the state of those particular lines. We'll explain why that is the case. A single pin is called a read-write line, or the read-write pin, it specifies whether a pending operation is a read operation or a write operation. Of course, in this case, we're dealing with RAM chips, random access memory chips, and not ROM chips. In the case of a ROM chip, it is always a read operation. If it is written as R/W, in this case, a high voltage means a read operation, and a low voltage means a write operation. The slash has a particular meaning when you specify the label of a pin. The slash basically means negation. So in this case, it means /W is the state of the line. Not write is basically the state of the line, which also means if the line is high, it is not writing. If the line is low, it is specifying a write operation. All right. The chip select line of a memory chip is an enable pin. The pin is asserted, which means it is selected. The chip is selected if a memory chip is to perform a memory operation. Now, it will be clear why we need a chip select line later on. This means we can specify the address pins and read-write pins all we want, but if the chip select pin is not asserted, then the memory chip will simply ignore. It's standing there, it's interpreting all the signals, but it's not doing anything because nobody tells it to actually do anything. Okay, so it'll be clear, how all of these things, connect. The memory system. The memory of most computers consists of multiple memory chips. In the simplest case, we can assume all memory chips are of the same size. Okay? And all the address pins of all the memory chips are tied, which means A0, the bit 0 of the address line of all the memory chips are all connected electrically. A1 goes to all the different memory chips, A2 goes to all the memory chips. Are we doing okay so far with this? I'm not sure whether I have a picture. I used to have a picture with my previous presentation of the same stuff, but it's not here anymore. That means if I want to draw a picture, let's say we have two memory chips in this case, and let's say we have the signal A0 coming in from the MMU, the memory management unit from the processor. This line, which is a copper line, goes to the first chip. It also goes to the second chip. It's the same signal. And you have A1 connected to both chips, A2 connected to both chips, and so on. Yeah.
So that's why you need that
chip select.
Chip select.
Exactly. I will give you guys an analogy after this, and it will be all clear, how this all works out. All right, and this also applies to data pins and also the read-write pins. In other words, the address lines, the data lines, the read-write line, they are all shared by all the chips. Okay? That seems to be kind of odd, right? The read-write line we can kind of understand, but the data line, being shared by all the memory chips, and the address line being shared by all the memory chips, it doesn't seem to make any sense. I mean, doesn't that cause problems down the line? Well, let's take a look at this example. The chip select pin of each memory chip is connected separately to a memory management unit. It's usually a component inside the processor these days, but in the good old days, the MMU is a separate chip from the actual processor chip. But these days they're all integrated into the same chip, so you can't really see the MMU anymore because it is inside the same Pentium processor that you put into your system. Okay? But the most important part is each memory chip has its own chip select line connected separately to the MMU. That's the only one part that is individual of the memory chips. The MMU is usually integrated into a CPU these days, although in certain architectures it is actually physically separated from the CPU. It's getting harder and harder to find an architecture where the MMU is separated physically from the CPU itself. One function of the MMU is to figure out which memory chip should be used based on an address. All right, so this part gets interesting, and I will use an analogy later. Let's make the assumption as follows. Each memory chip has 2 to the power of 9, which is 512 locations. Okay? Each location is 1 byte. And the system has 8 such memory chips, and they're numbered chip 0 to chip 7. CS0, chipset 0, connects from the MMU to the first chip, and so on. Are we having a mental picture of how everything is connected? Okay, we have 8 separate memory chips. Each one has 512 bytes. It is byte addressable. And we have chip select 0 of the first chip connected to the MMU, and then we have CS1 of the second memory chip connected to the MMU separately, and so on. So there are 8 individual chip select lines connected to the MMU separately. From the hardware perspective, the actual size of memory is 4,096 bytes. Even though each chip only has 512 bytes, we have 8 of these, and 8 times 512 is 4,096. So we have a total memory space of 4,096 bytes. From the software perspective, that's exactly how much RAM you can play with in software. Okay? That means, an instruction should be able to address any one of the 4,096 locations. The memory space is from byte location 0 to location 4,095. Okay, it's in 4,095 because we counted from 0 and not counting from 1. All right. If an instruction wants to access a location X, assuming location X is somewhere between 0 and 4,095, the question is, now what does the MMU have to do in order to access that single location X? Well, the first thing we'll do is to find out which chip we have to deal with. The chip number that we have to deal with is given by X divided by 512, and then you take the floor of that number. What does that give me? If X is from 0 to 4,095, what is the range of value that this expression is giving me? The floor of X divided by 512. It will be from 0 to 7. Okay, which is great, which is exactly what we want. Okay. Once we identify the chip number, we have to determine the address of location on the chip itself. Let's go through an example. And since I'm recording, I'll just go ahead and use Notepad as my whiteboard. And we have to do the font thing every single time. After today, I'm going to switch back to Linux, when I teach the class, so I don't have to use Windows tools. All right, let's go ahead and try to figure out what we have to do if we want to access location 3050. Okay, this is the location that I want to access. Which chip contains this location? That's the first question. The chip number is given by this expression, the floor of 5,050 divided by 512. And what exactly is that number? I think this is 5.
Yeah.
Not 6, this is 5. Because you need at least 3,072 to have a 6 as the quotient of the number. Yep.
So no matter how close this was to 6, if it's not 6, it will drop all the way down to 5?
Yes, this is a floor function, and what a floor function does is it will return the largest integer that is less than or equal to the number that you put in the parentheses. In other words, it always rounds down. It never rounds up. All right, so this will give me, chip number 5. Now, what location do we have to access on chip number 5? Well, that turns out to be a pretty easy question to answer because, okay, location, localhost, location on chip 5 is equals to 3050 mod 512. That will give me the location on that chip that I want to access. And that turns out to be would that be? It's the same as this minus 5 times 512, and that's what? Arithmetics, I can't do it.
390. 390, 490.
490? That sounds about right.
Yes, 490.
Okay, 490. Okay, so given this information, I now know how to deal with the address lines, and let's go ahead and move on to the next slide. Memory cycles. Okay, so we'll continue to use that example, and we'll go through what a memory cycle is. Let's say that the software wants to write to that location. It wants to change the content at that location. From the software perspective, it is location 3050. In other words, when you write a program, you are writing in assembly language and say, I want to change location 3050 to something else. The question now is, how does the MMU manipulate the memory chips so that the new content is stored at that location? First of all, the MMU has to compute the chip number and the address on the chip. We have just done that, right? If I go back and look at Notepad, we have just performed the calculation to compute the chip number, which is using the division, and then you take the floor function of that. And then the address on the chip is going to be the location that you want to access, and then you mod it with the capacity of the chip. Is that okay so far? Okay. Next, the MMU is going to latch the address onto the address lines. In other words, the MMU is going to quote-unquote drive the state of the address lines. It will output high and low voltages, and the memory chip is being passive. It's only listening to the address lines. But remember, not only chip number 5 is listening, all 8 memory chips are all listening to the address lines. So they're all listening and say, oh, okay, location 490, expressed as a binary number. But nobody is doing anything just yet. Okay, they are all listening, and they all say, okay, location 490 as a decimal number, but no one is doing anything just yet at this point. Yes?
Just a quick question to make it clear. Like, if X is lower than 512, it will be on the chip 0 no matter what?
If the location is less than 512, there will be location 0, yes.
Okay.
The read-write line will then be turned low to specify this is a write operation, just like in the previous slide. A low signal in this case means a write operation. And then the MMU will also specify the new content of the location onto the data lines. In other words, if the new content of that memory location is supposed to be, let's say, A6 in hexadecimal, then the binary bit pattern of did I say A6? A6 would be 10100110. Okay, so that particular bit pattern will be driven by the MMU so that the memory, the data lines will have exactly that particular pattern. Now, of course, when you're talking about voltages on the line, you can only specify high and low and not necessarily zeros and ones. So it will be high, low, low, high, low on the 6 data lines. And then the chip select line will have to be asserted to say, because right now we have 8 memory chips. They're all listening to the address lines as well as the data lines. Okay, but I only want to write that single byte to only one of the memory chips, not all 8 memory chips. So at this point, now that everything is specified, the memory chip corresponding to chip number 5 is going to be asserted. Now I use the word asserted instead of saying it is high, low, 1, or 0, because the chip select line is what we call an active low signal. Active low means if the voltage is high, the chip is not selected. The chip is selected only if the voltage on that line is low. That's why it's called an active low signal. But in this class, from the software perspective, we don't really care whether physically it has to be high or low voltage to mean, yes, you are the one selected. We just say whether it is asserted or not. Are we okay with that concept? Asserted means, yes, I'm talking to you. Okay. So now we are talking to chip number 5, and chip number 5 is the only one who has to pay attention now. The selected chip will now say, oh, okay, I guess I am the one who has to do something. So the memory chip will now sample the address lines. In other words, only at this point, the memory chip will say, okay, now I'm paying attention to the content that is already on the address line. In this case, it is 490 expressed as a binary number. So from that, it can determine which location will receive the new content. And then shortly after that, the selected memory chip will also connect the data lines to the location that is specified. In other words, it will be sensing the voltages on the data line and then use that to update the specified location on that particular chip. Okay. Now all of this stuff here takes time. There's a certain delay, because of each step. The selected memory chip will connect. Okay, we just talked about step number 7, and then on step number 8, the selected location is overwritten by the content specified on the data lines, which is just something that I talked about. Now you have to remember, some steps here cannot be observed externally. In other words, in this particular case, if you use an oscilloscope or some other means, you can only observe everything up to step number 5. If you put an oscilloscope on the chip select line, yes, you will see the voltage change at step number 5. But after step number 5, in step 6, 7, and 8, there's no observable output from the external point of view, because everything is happening inside the memory chip. The MMU has no idea when the memory chip is done writing to that memory location. All right. Now this is a very, very important concept, because this is why we have latency. When you buy memory chips, they have certain types of latency, different classes of latency. This is one type of latency. From the time the chip select line is asserted, how long does it take for the memory chip to reliably change the content of a location? That's what we call a write latency. Yep.
Is that related to the chip timing?
It has to do with chip timing. It has to do with the transistor size of the chip. It has to do with a lot of factors.
Like the CAS and the RAS numbers?
Right. Those numbers are definitely related to this. Now, I cannot remember which one is exactly which one, but they're all basically internal cycles that are needed in order for the operation to complete successfully.
Okay.
Yep.
Is it connected with memberships like DDR2 type, DDR3 type, and like 1 megabyte L cache and all that?
DDR has nothing to do with what we are talking about yet. Okay, so we'll talk about DDR. I'll just kind of throw in something about DDR technology after we talk about this. Okay. So as steps 6, 7, and 8 happen, the MMU is the one that has to sit around and say, okay, I cannot start the next memory cycle. I have to wait, and that's what the wait. The latency is about the wait state. This is called the wait states. In other words, if you have a slow memory chip, you have to tell the MMU and say, well, this is a pretty slow memory chip, so count to 5 before you start the next memory cycle. If you have a fast memory chip, maybe you only have to count to 2. That's called the wait state of a memory chip. Okay. So at some point, after the number of wait states, the MMU will basically say, okay, I think the operation is done. Now remember what I said. The MMU will say, I think the operation is done after a certain delay. It does not know actually whether the operation is done or not. Okay, and that's why if you program your BIOS with the wrong wait state or wrong latency, you can run into interesting problems. You'll be lucky if it doesn't work at all, because then you can just say, okay, I guess that just doesn't work. A worst scenario is it works marginally, because latency changes based on a lot of factors. Temperature is one of the factors. And I guess memory chips also change their nature over time. All silicon stuff changed their nature over time because the impurity inside the PN junction, they actually continue to diffuse over time, so the latency can actually change over time with no external factors being changed. So that means your computer can work just fine. You can say, oh, I just overclocked this machine to no end, and it works perfectly fine. And the next day, it may not work at all. Or it may fail only on certain locations. Only when you write to certain locations, just by accident, it just missed that one timing, and it fails. Okay? So those are really bad problems because they're not easily reproduced and they're not deterministic. Sometimes it depends on the phase of the moon, cosmic radiation, stuff like that can all have some factors, can all play into this. So when the MMU thinks the whole thing is over, it will stop driving the data lines, it will stop driving the address lines, and the memory cycle is concluded. Are we doing okay so far with a write cycle? A read cycle is about the same. It is just as tedious, except the read-write line is high in order to specify a read operation. And then also, if you look at this, the data lines is no longer driven by the MMU because this is a read operation from the perspective of the processor. If the processor is reading from the memory chip, the processor should not be driving the data lines. So instead, the selected location of the memory chip connects to the data line, driving the data lines based on the memory content. This is done by the memory chip itself. So in this case, the memory chip is the one that is driving the data lines. The MMU still has to wait for a certain amount of time because it doesn't know exactly when content is reliably driven on the data line. So there's a certain delay. So you count 1, 2, 3, 4, 5, and then the MMU will say, okay, 5 wait states is over. It is time to sample the data lines. So at that time, it will sample the data line and read the content. After it reads the content, it will feed either the ALU or do something with the content of the data line. And then at that point, the MMU can stop, can release the chip select line, which basically tells the memory chip and say, okay, you're done. There's nothing to do. Stop driving the data line. The selected memory chip will then stop driving the data line. The address line will stop. The MMU will stop driving the address lines, and the memory cycle is done. It's ready for the next cycle. Yep.
What tells the memory chip to get the data?
To get the data?
Yeah.
When you assert the chip select line.
Oh, okay. When it's
So-
in the read cycle,
When it's in the read cycle.
and then it does chip select, that's when it goes to go get it.
Yeah.
Okay.
So imagine this. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 people on the first row. So each person can represent a memory chip. So imagine each one of you has a notebook with exactly 512 pages. And each notebook is numbered from 0 to 511. Okay? So me, being the CPU, I have access to 8 times 512, which is 4,096 locations, or pages in this analogy. Is that okay so far? But in order for me to access a particular page out of the 8 notebooks that is contained by 8 memory chips, I will say, okay, I want the content of page 490. All 8 of you, will hear that. Okay? It's only when I say, oh, I don't need it from the rest of you, I want it from you. Okay? Then only you will reply with the content of page 490 in your notebook. Okay? And that's the read operation. What happens when the MMU does something wrong and it asserts multiple chips? In other words, your chip select line is asserted, and by the way, your chip select line is also asserted. Then we have what we call a bus fight. Okay, it's called a bus fight. It's not a fight inside the bus because It's called a bus fight because the address lines collectively is called the address bus, and the data lines collectively is called the data bus. So in that case, you'll be screaming out the content of your page 490, and you'll be screaming out the content of your page 90. Now, in an environment like this, physically, it's not a problem. It would just be garbled from my perspective. But no damage is done, no harm is done. But remember, when you're doing this inside a computer on a circuit board, what exactly is saying, oh, the location should be a 1? You're driving the data line high, right? What if that particular bit is low from your perspective? So you want to drive that line low. So one guy is trying to drive it high, meaning you're putting effort into changing the state of the line to a high voltage, and you are putting effort into driving the line low. So now we have a little wrestling going on there, okay? And whenever you have a chip trying to drive high and another chip trying to drive low the same line, you have a lot of current going between those two chips. What does current do to chips? It heats it up, exactly. And so when you have a bus fight, a lot of times something will get damaged. Okay.
Another good reason not to ride the bus.
That's right. All right. So are we doing okay in terms of the concepts of a memory write cycle and a memory read cycle? That's this has been the way things have been done since the early days of digital computers, and it still has not changed. In other words, when your Pentium processor is trying to access one out of the 8 giga locations, 8 billion locations, it still has to go through this. The changes is what? The number of address lines. Okay, it is a lot larger now compared to before, and also the width of each location is also a lot bigger. What is the width of one access these days? Go ahead.
The CPU is coded for 32-bit or 64-bit instructions.
Right.
But the memory chips can be used independently, either on 32-bit or 64-bit system. So in a 32-bit system where the 32-bit chip, it issues a 32-bit address, will the 64-bit address lines on the chip remain zeros, or?
That's a good question. Okay, I was just about to answer that question. Okay, you can have a processor that only has 32-bit data lines. In other words, from the processor's perspective, it can only read 32 bits at a time. But remember, your processor is not directly connected to the memory chips. In the good old days, they're going through a north bridge. So the north bridge, can do some tricks to speed up operations. In other words, the north bridge can get, the processor's, demand of saying, I want to access location, blah, blah, blah. Okay, but the processor is only asking for 32-bit content, or the width of the location is only 32-bit. The north bridge in this case will say, well, I can actually access 64-bit at a time. Okay, because you have dual channel. Okay, you have dual channel, so you can access your memory at twice the width, compared to a single channel. But it's up to the north bridge to handle that situation. So the north bridge will actually get 64-bit at a time, but it will only present 32-bit to the processor. But when the processor asks for the next location, guess what? The north bridge doesn't need to do anything anymore, because it says, I got those 32-bit already. Here it is. And that's why dual channel makes things faster, is because it's accessing twice as much memory for each memory cycle.
Do they have to be adjacent memory locations?
They have to be at adjacent locations, yes. Now that's one way to speed up operations, but it can only speed up so many times. When you look at the memory cycle, which is the same thing that has to happen with your super duper memory Pentium chips, a lot of time is wasted by the address line. Okay, because every location, in order to access a single location, you have to specify the address, and then you have to do the chip select, and then you have to wait a little bit, and then you either do the read operation or the write operation, and so on and so forth. So what is DDR? How does DDR work? Double data rate. Double data rate only works in burst mode. In other words, if I know ahead of time that my next location is adjacent to the first one and the next one is adjacent to the second one. In other words, if I know I want to read 16 consecutive memory locations, maybe I can do some tricks here. In other words, I can do some trick and then tell the first cycle is still kind of conventional. Okay, you have to tell the memory chip where I'm starting, okay, the starting location. But then the consecutive cycles, you can go into the DDR mode or the burst mode, in which there's an additional line to the memory chip indicating this is a burst mode operation. And then in that case, the memory chip is keeping track of what was the last location accessed. And then for each chip select cycle, it will say, oh, last time it was 490, so this time it's 491. So the processor or the MMU does not need to latch out the address again and again and again. And that's why it can go faster this way, because it is assumed by the memory chip that the next cycle is accessing an adjacent or the next location. Okay? So that's why DDR is faster. DDR2 is even faster because it is using both the rising edge and the falling edge of a clock. And then DDR3 is faster. I think it's because they can interpolate, the in-between states between the rising edge and the falling edges. But once again, it only works when you're accessing in burst mode. It does not work when you're accessing random locations. Okay, if your program calls for random locations all over the place, DDR is not going to be very helpful because you're not reading consecutive locations. On the other hand, if you're working with, let's say, merge sort or some other algorithms that involves scanning through an entire array sequentially, yes, DDR will be very helpful in that case. DDR also works very well with caching because the cache inside the processor or each unit of cache is not really just 32-bit or 64-bit. Okay, the cache keeps track of quote-unquote pages. And each page, I think, is 16 locations, or some, it's not 64-bit, it's some larger amount of pages. So when you try to read content into the page, you're not really just reading one location and say cache it, reading another location and cache it. You're reading a block and say cache the entire block. So that's why the burst mode really helps when it comes to working in conjunction with caching. Any questions about DDR type technology versus the cache and how it is speeding up the operations? No questions? Okay. All right. So now you can go back to your data structure class, and when there are two algorithms with the same order, with the same big O notation, in other words, in theory, they're both the same speed. They should be equally fast. You can now tell Mr. Fox and say, aha, but. But since this algorithm involves a lot of random location read and writes, it's going to be slower because you'll be blowing the cache and you won't be using the DDR or the burst mode of operation as much as another algorithm which is only performing sequential operations. And that's why merge sort is so nice. How many of you know what is merge sort? As opposed to quick sort or heap sort. Quick sort and heap sort have random access all over the place. Even though the speed is theoretically speaking the same as the merge sort, they can be slower because you're blowing the cache left and right. You're not performing sequential operations. There's no locality to the way that you're accessing memory. All right, but that's stuff left for another class another day. Any questions with this slide? No questions? And I think this might be it. Oh, okay, we have to talk about the cache a little bit. The cache is a special type of memory that sits between the processor and memory, but it is not registers. A cache can be seen as a special type of associative memory, associating a physical address to its content. It's basically like a lookup thing. Okay, So a cache is a lookup mechanism. You can ask the cache, what is the content of physical location, blah, blah, blah. If the cache has that location cached, it will just reply without having to go out to the memory bus. But if that location is not cached, then the MMU has to go out and actually grab the content from memory in order to answer the question. Now, cache is expensive in terms of the number of silicons. So that's why you cannot have a lot of cache, and that's why processors with a lot of cache can be charged a lot more money, okay? Because it is a very desirable feature. And also, caches can be separated into different levels. Level 1 cache is closest to the processor. Level 2, level 3, will be further away from the processor. So they're basically slower, but they're still fast, much faster than accessing memory directly. Are there any questions about caching? No. Okay. So what happens when you have what is the maximum number of cores per processor these days? 16. So you can actually buy a chip off the shelf with 16 cores. Sorry?
It's a server chip.
Is it a Xeon?
No.
Or
AMD. It's
AMD? Okay. What about Xeons?
They're up to 10 or 12 now.
10 or 12?
I think it's 12.
Okay. So what if you have a multi-core processor that is super duper like that, but it only has, well, let's say 1 meg of cache?
You're gonna have some throttling issues.
So most of the cores will be twiddling their thumbs because memory cannot feed instructions or data fast enough to keep the cores working all the time. Okay, so when anyone wants to buy a multi-core processor, they really need to look into the amount of cache available to the processor, because without proper caching, 8 cores really doesn't do you any good. Yep.
Memory controller has a lot to do with that too, like the way the bus operates and so on.
Yep. But you're still going to the same memory system, so that's why you still have a bottleneck with accessing memory, and caching is the only way you can kind of quote unquote get around that problem. Yep.
On like multi-core design, would they each have their own level 1, level 2 cache systems that my level 3 would be shared among all of them?
I think it's a design decision of each individual chip and manufacturer. So you can have designs that have shared, and you can have designs that are not shared. Yep.
I think the way it currently works is 2 cores or 4 cores will share an L2 cache, and they'll
Okay.
have individual L1 caches. And then the L3 cache is a pool for the entire chip.
Okay.
And the only one, no, never mind.
Yeah, a lot of that has to do with the type of application that people run. Can you kind of keep some of the cores on the same task so they share the same memory space? Because if you can, then they can share the same cache and everything will be very effective. But on the other hand, if all the cores are working on completely different things, accessing completely different regions of the memory space, then you have a different issue. You have a different problem in that case. Okay. So there's a lot to go into how to utilize all the processor cores inside a multi-core processor, because without more careful software consideration, the hardware can only be pushed to a certain point. But if you can plan how you use the cores carefully, you can extract a lot more performance out of the same processor once you understand how the hardware is organized. And that's why compilers, there's a long way for compilers to catch up with technology, with hardware technology, because right now GCC doesn't care. It doesn't ask you. There's no option to GCC to say, I want to compile this program assuming there are 4 cores, or assuming there are 2 cores, so that you can utilize the 2 cores more effectively. If the compiler assumes it's a single core. All right, let's move on. So we just talked about caching, burst mode memory access. That's our DDR discussion. We have just talked about that. The DDR technology is really just another name. The actual technology is called SDRAM, or Synchronous Dynamic Random Access Memory. All DDR technology falls into this category of memory access, and that's basically what we just talked about. Accessing I/O. Okay, well, this is something that's different. What we have talked about so far up to this point, including the analogy, deals with memory. Okay, and we all know about memory. I mean, chips that you buy, the DIMMs that you buy and put into a computer, that's memory. What about input-output? What if my computer has, a super-duper processor, lots of cache, lots of registers, lots of memory, but there's no I/O in the system? What do I have in that case?
A whole lot of nothing.
It's a space heater. I have a good space heater there because why? Why do we need I/O?
So you
That's how you interact with the computer.
So that we can get information or data in and get data out. Okay, it can be something as slow as a keyboard. Okay, completely limited by how fast I can type. It can be the network interface. It can be the hard drive controller. Okay, your SATA controller falls into the category of I/O, input-output devices. Okay, and that's important because without a hard drive controller, most computers are completely useless. Okay, I/O can also include other types of input. Think about the anti-lock mechanism or the anti-lock controller of your car. What is the input to that computer? How the travel of your brake pedal is one input. The rotation of each individual wheel is another type of input. And it can take other stuff too, like I think some of the newer cars also have sensors to sense, what is the lateral G, of the car. It can sense, a lot of other things too, because it can sense whether your car is actually rotating like this or not. Is it called yoke control? Something along that line. I think the Evo, has that, since from a very early time. But now most cars have some form of a stability control. Okay, and all of that are basically inputs as well. It's just not our conventional type of input. Look at your cell phone. Your cell phone has more types of input than probably your desktop or your laptop computer. Because you have what? You have GPS, you have the compass, you have the accelerometer. What else do you have on the cell phone that is usually not on a regular computer?
Well, I was going to say microphone.
A microphone, the camera, 2 cameras in most cases.
Cell radio.
Okay, touch screen, yeah. So if you think about that, your cell phone actually has more technology than your laptop or your notebook computer. Okay. Now, how do we access, how do we deal with I/O in this case? We have just talked about how to deal with memory, but I need to get something into memory to begin with in order to run a program and to process information. How do we get that information into the system? Well, these are called I/O operations. Okay, input-output operations. And there are 2 ways for processors to access input-output devices. The first method is called memory mapped I/O. This is kind of interesting, and it is not used by Intel processors. Memory mapped I/O basically says within the entire memory space, I will reserve certain parts of the memory space so that those locations, when I write to location 516, I'm not actually changing the location of a RAM module. Instead, I'm actually talking to, let's say, the network card. If I write to location 968, I'm not actually writing to a memory location. I'm not, dealing with a memory chip. I'm actually, talking to, let's say, the SATA controller. That's called memory mapped I/O because the input-output devices are quote-unquote mapped to memory locations. Question?
Intel uses MMIO.
Intel uses special I/O locations, not memory mapped I/O. I'll explain that later. It's the next one is I/O mapped I/O. I know the name is kind of strange. It's input-output mapped input-output. So basically, this is used by most Intel processors, and including all the relatives of the x86 family. In this case, if you want to access input-output locations, you need a different set of instructions. In other words, we have one set of instructions to deal with memory, and we have another set of instructions to deal with input-output. Does everybody understand how this is different from the previous approach? The previous approach means we only have one set of instructions. They can only deal with memory. But parts of the memory space is actually mapped to I/O devices. So when I read from a certain location, I'm not really reading from memory chips. Instead, I'm asking an I/O device for its status. But when you have I/O mapped, mechanism, the mechanism of I/O mapping, that means you have two separate sets of instructions. One set of instructions deals with memory, exclusively, and the other set of instruction will deal with input-output devices exclusively. Now, by that, it is also implied that your input-output space is separated from your memory space. In other words, you have memory location 0, and then you have I/O location 0, and they have nothing to do with each other. Yes?
What about when you're dealing with a component that accesses different hardware components? For instance, your monitor would access both your video card, and it would need input from the processor. So how does that work?
Say that again. I think I got your question, but I want to be sure.
Your monitor
Yes.
requires a feed from the video card, but also the processor will update that feed. So how does that work?
Okay, your monitor is driven by either the VGA or your DVI or your HDMI, cable, and that is driven by your memory chip. Your video chips, or your dedicated video card. In other words, the processor really cannot talk directly to the monitor. The processor has to talk to your video card, your VGA controller, or whatnot, and then that can now talk to your monitor to get the name of the monitor and stuff like that. Because VESA is a two-way communication. It's not only sending pixels out to the monitor, but you can also ask information back and say, what is your native resolution, and so on and so forth. But it's actually doing that through the VGA or the video chipset.
Okay, so there's I/O instructions for the video card, but not for the monitor.
It gets a little bit more complicated than that when you're dealing with high-speed devices, like your video card and also your SATA card. Now, if you have to feed every byte to your SATA controller in order to write to a hard drive, the I/O operations will be very, very, very slow, right? So instead of doing that, the I/O instructions will only be used to specify, hey, SATA controller, I want you to go to sector da-da-da-da-da, that's a hardware, hard drive, kind of thing, and I want to read, 6 megabytes, and this is the memory location, the beginning of memory location where those 6 megabytes have to go.
And then there's another processor on the SATA controller.
Exactly. The SATA controller can access memory directly, just like a processor can. Okay? That's called DMA, or direct memory access. Okay? That's what DMA stands for. Yep.
And your VGA has DMA as well?
The VGA is even different. It's more different than that because it depends on your memory chip. In some systems, your VGA chipset can share the memory space with your processor, so it can basically quote unquote steal or use a portion of your regular memory space for display purposes. Now those are typically your lower end processors,
Sure.
but the high end processors definitely have their own memory inside the video controller. Because high-end video cards are really, really different, completely different from the low-end ones. The high-end ones, what you're communicating to the video card, you can send over like texture maps and stuff like that, through the I/O operations or through DMA. But you're also telling the graphics card that I want to view everything from this angle. And then the rendering is completely done by the video card itself. So the video card is keeping track of the objects that you have in that space, it's keeping track of light sources and stuff like that. And all you're doing from the processor is to say, oh, okay, I want to change that object location from here to here, and I want to change the view from here to here, or I want to change the light source from this to this. And then the rest of the rendering is completely done by your video processor itself.
Instructions for the video card
Mhm.
are on the hard drive or main memory now.
It can, okay, a part of that is probably on the video card itself to bootstrap, stuff with. The rest of it can come from your operating system. I'm not 100% sure, how that works, but I think it is runtime programmable. In other words, whatever is on the chip or on the card itself can be overwritten at runtime by additional instructions. And that's why people like PS3s, you guys know that, I think it's the Air Force who bought a whole bunch of PS3s and turned them into a cluster. And they were doing heavy-duty computations using PS3s, PlayStation 3s. And of course, they were not very happy when Sony said, no more third-party support.
Yeah.
Do you guys kind of keep track of that stuff? Yeah?
Yeah.
Okay. Yep.
I don't understand how can they deny certain modifications to the systems that you personally own.
I know that.
Okay, go ahead.
It has to do with, they own the firmware on the PlayStation.
Yeah.
And so the way that you put another operating system on the PlayStation, that's how you'd run these programs, is you'd have to alter the firmware.
Mm-hmm.
And that's how they changed it. They made changes to the firmware so that you couldn't get into it.
Right. Now, you can also, hackers can easily go into the firmware and find out, how they protected the firmware and, basically prevent Sony from updating your firmware. But if anyone tries to do that, at least in the United States, they'll be in violation with, in terms of the DMCA, the Digital Millennium Copyright Act, because any attempt to circumvent copy protection mechanisms, in this case, it's the protection of the firmware itself, is criminal. And they can arrest those people. And that's why the guy who came up with the method to circumvent the Sony protection was he actually sentenced? He was arrested for sure. Was he actually sentenced to jail?
The guy that broke CSS?
No, not CSS, PS3, the PlayStation 3 protection.
Are we talking George Cox?
Yeah.
Yeah, I was just mentioning that and I don't remember if it was sentenced.
Oh, okay.
And I know he got like sued or something.
Yeah, he
So
got
it's
into a
really
big mess. He got into a big mess, and then people were tricking Sony executives to tell to display the what was it? Is it the code to the key to unlock it? Yeah, they tricked the CEO to use Facebook or Twitter to tweet it out. Anyway, it was a big mess. It's. All right, we're done with logical memory space. This is the last part. Now, this module does not include any discussion of virtual memory. Okay. In other words, we are only talking about physical memory. We're not talking about virtual memory. Virtual memory adds another layer of complexity to the whole game. But if I want to describe virtual memory in a nutshell, it's basically swapping in and swapping out. From the software perspective, you may have 16 gigabytes of RAM, but you only have physically 4 gigs of RAM. So how can that happen? Well, when you use up all 4 gigs of RAM, so initially, all your memory is actually physical. But when you run out of 4 gigs, then what the operating system will do and will say is it will select portions of your memory and say, oh, you haven't really used this for a while. I guess you won't need it in the near future. So what it will do is it will copy the entire block. A block size can be in maybe 4 kilobytes, maybe bigger, smaller. It doesn't matter. But it will copy the entire block of memory from your memory chip to your hard drive. So now it frees up that portion of memory, and it will map your virtual memory from somewhere into the physical memory, so that your program can run using that chunk of memory as if it is just regular memory. But later on, what if you need that block back? It will swap it back in. Okay, so all this swapping will incur a lot of latency because going in and out of the hard drive is a slow operation compared to regular memory access. And that's why even though in Windows and Linux and most modern operating system, you can set up to have a certain amount of virtual memory. My personal feeling is if you ever need to get into the virtual memory part, the performance of your computer is going really down the drain at that point. Okay? But we are not going to talk about this in this class. This topic was actually covered when I took assembly language programming. They actually talked about how the hardware works in conjunction with your operating system to implement virtual memory. And that was from San Francisco State University, which is not even famous for its computer science. Then again, in that case, the class size went from 60 down to maybe 15 or 12 at the end of the semester. It was a fun class. I really liked that class. That's also back in the time when we had dedicated terminals.
Nice.
There were 4. Okay, there were 4 dedicated terminals that people can use to do their homework assignment. There were 60 students to begin with.
Wow.
So when they have to do the homework assignments, they have to do it in one of the 4 terminals. And I'm not talking about terminals like PuTTY or anything like that. We're talking about plain text terminals. You can have one session at a time. You can see one screen at a time. I always get my assignment done like within 2 days of the assignment, so I never really run into problems with scheduling and stuff like that. But if I go into the lab, like 2 days before an assignment is due, there's a sign-up sheet like this long, and people are waiting along the hallway, for their turn to use the terminals for 15 minutes or half an hour. Then they have to give up. It's a round-robin type of scheduling. So if you cannot get your part done within the allocated amount of time, you can go back to the end of the line and line up again. Yep, that's the good old days. You don't get your own virtual machine, slow or fast. So don't complain if your virtual machine seems to be a little bit slow. All right, so we are almost out of time. We are out of time, actually. And so what I'll do is I'll just tell you what else you have to do over the weekend. We are done talking about adding, arithmetic operations. Wait, no, we're here. Okay, my bad. Okay, you might want to read half adding and full adding. This one is particularly interesting to people who want to get into electrical engineering as well as computer engineering. If you want to do more on the hardware side, that's a very interesting topic. I'm not going to talk about it in the class. I might actually just kind of skim through the topic a little bit. But it is very, very related to what we have just talked about in terms of binary addition and subtraction. If you have any intention to go into hardware or want to understand more about what is happening inside the processor, that would be a good topic to go over. The rest of the class, or if you're not interested in that, you should move on, go to topic number 2, and start reading addressing modes and memory allocation, and also the other 2 slides. Okay, so we are actually getting into instructions for the i386 at this point next week. Okay, so we will be dealing with all those confusing memory addressing modes, and if you do not remember what a pointer is in C, this is a good time to brush up on pointers. All right, I'll see some of you over at the lab. Okay.
So George Hawkins is hired by Facebook.
Oh, he caused that.
Like I said.